Right, we're going to look at the section now, which is about e to the power of minus something. E to the minus, that's how I've sort of expressed it in the mind map. And why is this a significant thing? Well, this is a significant thing because if I go 1.1 to the power of 10, then 1.01 to the power of 100, then 1.001 to the power of 1000, okay, it tends to e. Okay, you can check that on a spreadsheet. And as a sort of related concept, if I've got y equals e to the x, then that implies that dy by dx equals e to the x as well. Okay, as distinct from if y equals 2 to the x, then dy by dx does not equal 2 to the x. In fact, it equals 2 to the x times log 2. Okay, so you could not bother with the number e and just use some other base, but if you're using some other base, you're going to get this extra factor floating around half the time. So e makes life easy. Okay, that's really the thing, because it has this quality of being the limiting point. If you're getting interest continuously, it has this quality of being the limiting point. So let's remind ourselves where we saw e before. We saw it in this context that 1 over 1 plus I is equal to v is equal to e to the minus delta is equal to 1 minus d. Okay, now I said that one's not terribly important. That's just notationally convenient. But really what we're dealing with here is this is equal to this, and if you generalize it for different times t, okay, that is e to the minus delta t. And what you notice is that this is really a special case because we're assuming delta is constant. But this is where this process becomes more powerful, because there I'm just assuming all the time delta is constant, the force of interest is constant. Let's just remind ourselves what we call delta, okay? So delta we call the force of interest, which is analogous to the force of mortality, which we'll see later. But notice this, if I integrate the constant delta between 0 and t, okay, if I integrate between 0 and t the constant delta with respect to some other integrating variable, say tau, that is equal to delta t. Okay, that's equal to delta t minus delta times 0, okay, which equals delta t. And that is revealing quite a deep truism here, that we don't actually need this to be constant. This expression assumes delta is constant, but we don't need it to be constant. If delta is varying, okay, so delta is a function of time, okay, then present value generalizes in quite a nice and neat way into e to the minus the integral between 0 and t of my force of interest delta at time tau d tau. Okay, and now the thing about this is we often can't integrate that very well anyway, but supposing we've got something fairly simple, supposing the force of interest is 4% and it's going down to 2% at a constant rate over the next say, well, suppose it's going down from 5% to 3% over the next 2 years. Let's see how we would deal with that. So delta times 0 is equal to 5%. That's the force of interest. Delta at time 2 is equal to 3%. And it reduces linearly over 2 years. Okay, so delta at time t is equal to 0.05 minus 0.01t. Okay, so question, what is the present value of £1 at time t equals 2? Okay, and all we've got to do is, if we think our present value, so the thing we need to think here, okay, present value is e to the minus delta t. Okay, but that thing is just the integral. It's just the integral in the special case that delta is not 0. So in our case, we're just going to integrate between 0 and 2, 0.05 minus 0.01t dt. And don't forget the minus in there because we're discounting. Okay, so that is nice and simple now. E 0.05t minus 0.005t squared between 0 and t and 2, and the minus is equal to e to the minus 0.1 plus 0.02. So t squared for 0.02, so that is equals e to the minus 0.08. Okay, which is equal to 0.923. Okay, is that sensible? Well, if it's going down from 5% to 3%, it's about 4% in the middle, so it's about 2 years, well, it's exactly 2 years of about 4%. Okay, so yes, that makes sense. So we can now deal with interest rates being variable, and we can just shove them all into this thing. So we just put whatever our variable interest rates are, okay, we can just shove them into there and do whatever we need to do. Okay, we could have, supposing now we had a question where we want to know what the interest rate, we want to know what the present value is at time 5. Okay, so same question. So time and delta, that's 5%, 3%, and we go 1, 2, 3, 4, 5. I suppose interest rates come down from 5% to 3% in 2 years, and then stay at 3% from there. Okay, and our question is the present value of £1 at t equals 5. Okay, well, all we've got to do is e to the minus the integral between 0 and 5 of delta of t dt. Okay, well, we just split that out now, we just break that up, so that's e to the minus 0 to 2 of 0.05 minus 0.01t dt. Okay, then we could multiply by e to the 2, or we just take off 2 to 5, 0.03 dt. So that's all we need to do if the interest rate's varying by different amounts. Okay, and you can easily work that out. Supposing then also I wasn't given it in that term, supposing I was given what the what the annual rate of interest I, then all I've got to do is convert I to delta. Okay, so supposing I'm told that the force of interest changes from 5% to 3% over those 2 years, and then the I rate of interest is 3% after that. Okay. So t equals 0 to 2, delta goes from 5% to 3%, then t is greater than 2, greater than or equal to 2, I is equal to 3%. Okay, well all I've got to do is t 0 to 2, delta of t equals 0.05 minus 0.01 t, and then t greater than 2. If I equals 3%, then 1 over 1.03, 101 plus I, is equal to e to the minus delta. Okay, therefore delta equals log 1.03. Okay, which will be a bit less than 3%. (2.956%). Which means I'm just going to do the same calculation as above, but I'm going to have 0.02956 in there. Okay, so once I understand what we're doing, we've got to once I understand what we're doing with our e to the minus whatever. So what I'm saying is here, once you put this in here, you just put the interest rates in here across time, and you can then do anything with it. You've got whatever power you need to calculate whatever present value you have. As long as you know the interest rate at each point in time, it doesn't matter whether you know it as the I or the delta, you can convert one to the other. If you know it at each point in time, you can calculate the present value of any payment you need.